Right, so this is the question number 1. This question appeared in December 2023 CSIT JRF-NET examination. The question is this: the isomerization of cyclopropane to cyclopropene follows Lindemann mechanism and is carried out in the high pressure limit. The ratio of the rate constant of activation to the deactivation step is 10, and that of the product formation to deactivation is 15. Given the effective rate constant is 150, the rate constant for the deactivation step is. Okay, so this is the information given. Now we have to find out the rate constant for the deactivation step. Okay. So here, isomerization of cyclopropane to propene. Listen, this reaction follows Lindemann mechanism. What is Lindemann mechanism? Suppose I take this reactant molecule as A, right? Lindemann mechanism is unimolecular collision will occur. So when two molecules of A collide, so that what will happen? One molecule get activated, the other molecule remains normal molecule. This activated molecule, okay, which undergo further reaction and form product. And this is the forward step is called activation step, and the backward step is called deactivation step. So let the rate constant for forward activation step be K1 and the deactivation step be K in -1, and the product forming step for this the rate constant be K2. Okay, and you know very well how to derive the expression for rate of the reaction, okay, for unimolecular reaction, right, as per Lindemann mechanism, right. So what is the rate expression? You know very well, rate of the reaction, let me write V. V means rate of this reaction, V is equal to K1 into K2 concentration of A power 2 divided by K minus 1 into A plus K2. This is the rate of the reaction, and we know very well experimental rate. What is the experimental rate? Experimental rate V is equal to experimental rate constant, also called effective rate constant, experimental rate constant into A. Okay, because it is unimolecular reaction. Right, this is the experimental rate. Now, since these two are supposed to be equal, if I equate these two, so I'll take this as left hand side and this is right. Okay, isn't this V and this V are one and the same? If I equate these two, what we get is K into A is equal to this quantity. K into A is equal to K1 into K2 into A square by K minus 1 into A plus K2. This we know. This A square can cancel. Therefore, the rate constant, see the rate constant for this unimolecular reaction is given as, okay, this is the rate constant for the unimolecular reaction, is given as K1 into K2 concentration of A by K minus 1 into concentration of A plus K2. Remember, this is the rate constant expression for Lindemann's unimolecular reaction. Okay, take down. Now we'll see what are the data given in the problem. The ratio of rate constant of the activation to deactivation step is given. Okay, rate constant ratio of the rate constants of activation step. Activation step rate constant is K1 to the deactivation step K minus 1. So K1 by K minus 1, this ratio is given, which is 10, and that of product formation to and that of product formation to deactivation. Product formation step rate constant is K2 and deactivation is K minus 1. This ratio is given as 15. Okay, and the effective rate constant is given, right? The effective rate constant is 150 per second. Okay, it's called effective rate constant. K effective is equal to 150 second inverse. We need to find out rate constant for the deactivation step, that is K minus 1 we need to find out. K minus 1. Yes, how to do this? Listen, how to do this problem? Listen. Now I'll take the reciprocal of this. I'll take reciprocal of this equation. Okay, so if we take reciprocal, what we get is that okay, one second. Here one more information is given, and the reaction is carried out in high pressure limit. The reaction is carried out in high pressure limit. High pressure means reactant concentration is high. When reactant concentration is high, then this value will be very high compared to K2, so you can neglect K2. So under high pressure limit, what will happen? See, under high pressure limit, this value, that is K minus 1 into A, this value is very much greater compared to K2, so we can neglect K2. Therefore, the unimolecular rate constant is equal to K1 into K2 by K minus 1. Since this is negligible, if you neglect K2, you will be getting K1 into K2A by K minus 1 to A. Okay. So A cancel, you will get this. This is nothing but effective. This is nothing but effective rate constant. Okay. So effective rate constant is equal to this quantity. Right? Keep this in mind. Very, very, very important. Now observe carefully. These are the ratios given. So first I will multiply these two. K1 into K minus 1. Then into K2 into K minus 1. I will multiply these two. If we multiply, we should multiply the values 10 into 15. I can write this as K1 into K2 by K minus 1 into 1 by K minus 1. So let me do it in the next page. Copy it. Let me just listen. What I did here is that, see, we have K1 by K minus 1, K2 by K minus 1 equal to 150, right? I just separated this into two. How? K1 into K2 by K minus 1 in one bracket and 1 by K minus 1 in another bracket. So if I do like that, I will get like this equation. What is K1 into K2 by K minus 1? It is nothing but effective rate constant. Effective rate constant is given as 150. So 150 into 1 by K minus 1 equal to 150. 150, 150 we cancel, we will get K minus 1 equal to 1. What is K minus 1? It is nothing but rate constant for the deactivation step. This is what we need to find out. Okay, so the correct option for this question is option B, second option. Right? Yes, this is the correct option for this option. Right? Take it. Okay. I just read out the question. This is question number 2. Two reactions have same pre-exponential factor, but activation energy of the first reaction is lower than that of the second reaction by 5 kilocalorie per mole. Given R value is 1.987 10 power minus 3 kilocalorie per mole per Kelvin. The ratio of the rate constant of the first and second reactions at 298 Kelvin is closest to. In this problem, they are asking the ratio of the rate constant of the first reaction and second reaction at 298 Kelvin. Okay, yes, how to proceed? Yeah, let me do it. Listen, this is a simple question actually. Two reactions, right? See, two reactions are given. First, we'll give you the data. two reactions are given and their pre-exponential factors are same. Okay, so let me take say reaction 1. For reaction 1 and for reaction 2, there are two reactions given. For these two reactions, pre-exponential factor A is same. Okay, but it is given that activation energy of the first reaction is lower. Activation energy of the first reaction is lower than that of the second reaction by 5 kilocalorie. What does it mean by that? Activation energy of the second reaction minus activation energy of the first reaction is equal to 5 kilocalorie, because the activation energy of the first reaction is lower than second by 5 kilocalorie per mole per Kelvin. This data is given. Then we need to find out the ratio of the rate constant for the first reaction to the second reaction at 219 Kelvin. So this is what we need to find out. Yes, how to do? Very simple. You know very well, for the first reaction, rate constant for the first reaction K1 equal to, according to Arrhenius equation, we can write this into K1 into e power minus EA1 by RT. Then for second reaction, K2 is equal to A into e power minus EA2 by RT. We want K1 by K2, so divide these two. So K1 by K2 equal to AA cancel. So in the numerator we have e power minus activation energy of the first reaction by RT, and in the denominator we have e power minus activation energy of the second reaction by RT. Okay, if you bring this to the numerator, so you will get, if you bring it to the numerator, this becomes plus, right? So we can write E. See, I have EA2 by RT. Here I have minus EA by RT. So if you take 1 by RT as common, we get activation energy of the second reaction minus activation energy of the first reaction. Okay, whole divided by RT. Whole divided by RT. Okay, the numerator, this EA2 minus EA1 by RT. Okay. Now, e power, what is EA2 minus EA1? EA2 minus EA1 is 5 kilocalorie per mole. 5 divided by R value also given in kilocalorie per mole. Okay, what's the value of R given? See, R value is also given in 1.987, 10 power minus 3 kilocalorie. So we can write as such. 1.987 is roughly 2. So let me use the value 2. 2 into 10 power minus 3. Okay, that's the value of R. And temperature is given as 298 Kelvin. 298 Kelvin. Okay, so this value we need to find out. But listen, you need not do this, right? Because in the computer-based examination, okay, calculator is available, so you can use calculator, right? I'll give you the final answer directly, right? Right? You will get the answer as 4640. So the correct option for this question is option A. This is the option. Okay? Take it. And this is the method. So this is question number 3. Listen, this question appeared in December 2023. According to Arrhenius equation, the plot that correctly describes the temperature dependence of the rate constant is. 4 options are given here. In option 1, K is plotted up against 1 by T. In option B, K is plotted 1 by T. Okay, in all the 4 options, K is plotted against 1 by T. Here, as 1 by T increases, there is an exponential decrease of K. Here, 1 by T increases, exponential increase of K. Not exponential, I'm sorry. Some increase in K is there. Here linear decrease, here linear increase, which is correct. Now listen, you know very well the Arrhenius equation. First write the Arrhenius equation, okay, and you will get the clarity. Listen, what is Arrhenius equation? You know very well Arrhenius equation K is equal to A into e to the power minus EA by RT. Okay, now we are plotting K in y-axis, 1 by temperature in x-axis. Okay, let me write this as K into e power minus EA by R into 1 by T. You can write like this. Now we are plotting K versus 1 by T actually, 1 by T. Okay, how the graph will look like? See, if I plot k in y-axis and 1 by t in x-axis, listen, as 1 by t increases, I have minus sign here. So exponential for minus, so it decreases in this manner. There is an exponential decrease in the rate constant is observed as 1 by t increases, not temperature, observe carefully. Not t, it is 1 by t. As 1 by t increases, rate constant decreases exponentially. Right? So the correct option among the four is option A. Rate constant versus 1 by t, there should be an exponential decrease in the rate constant. Right? Yes, this question appeared in June 2023. A reaction follows the rate law minus dA by dt equal to k into a square. Minus dA by dt is nothing but rate. K into a square is there, so it is a second order reaction. Starting from an initial concentration of A naught, the time taken for the concentration to reduce to A naught by 4, okay, namely quarter life of A is, so how to do this? Listen, it is given clearly second order reaction. You know very well, for second order reaction, the expression for rate constant is, okay, let me write here. It is a simple rate constant expression. Okay, see, for this type of differential equation, k into a square. Okay, if you do derivation, you will end up with this final expression. Rate constant k is equal to 1 by t times 1 by a minus 1 by a naught. This is the expression for rate constant, okay, for this type of differential equation. This differential equation we get if the reaction follows this type of reaction. 2A gives product. Okay, right. We'll discuss this in large extent in one of the class, right? But you know this expression for rate constant. Now, what we have to do, listen, starting from an initial concentration of A naught, initial concentration is A naught, then what will happen as the reaction progresses, concentration of the reactant decreases. At one particular time, the concentration becomes A naught by 4 times. At what time A naught becomes A naught by 4? This is what they are asking. Very simple. Listen, very simple how to do that. So k is equal to 1 by t into, listen, 1 by, here first I will put this. This is initial concentration, I will write like this. And listen, we need to find out the time when the concentration, remaining concentration becomes A naught by 4. Okay, this is the remaining concentration, that is A. Concentration at time t. Concentration at time t becomes A naught by 4. Okay, at one particular time, what is that time? That we need to find out. So bring the t here and k here. So t is equal to 1 by k into, now I'll just take the reciprocal of this, I'll get 4 by A naught minus 1 by A naught. Okay, take LCM, you'll get 4 minus 1 is 3, 3 by k into A naught. Right? When time becomes equal to 3 by rate constant into A naught, at this time, okay, a quarter of the initial concentration will decrease. Okay, will remain. Okay, only 1 quarter will remain. That means 3 by 4th amount will react. Okay, yes. So this is the time for 3 by 4th amount reacts from the given reactant. Okay. So the correct option for this question is option 4. 3 by k into A naught. Right? This question appeared in June 2022. The question is very simple. Carbonic anhydrase. See, whenever a name ends with ase, it is an enzyme. Carbonic anhydrase 2.5 into 10 power minus 9 mole per decimeter cube. This is the concentration given of the enzyme concentration. Catalyzes hydration of CO2 in red blood cells at pH 7.1 and 274 Kelvin. The rate of the reaction V reaches its maximum value when varied with the substrate S concentration according to the following equation. Okay. The question asked here is the catalytic efficiency of the enzyme in decimeter cube per mole per second is. Okay. See, rate versus substrate concentration relation is given. We need to find out the catalytic efficiency of the enzyme. Yes, this is how to do this. Okay, Michaelis-Menten equation. What is that? Rate of the reaction V is equal to K2 into E naught into concentration of the substrate by Km plus S. This is what we call as Michaelis-Menten equation. If we take reciprocal of this equation, we get 1 by V equal to, we'll get Km plus S in the numerator divided by K2 into E naught into S. You can separate this into two parts. How? Km by K2 into E naught into S plus S by this, S cancels, so 1 by K2 into E naught. We can separate like this. Okay, so let me write here 1 by V equal to Km by K2 into E naught. I'll write S separately, 1 into 1 by S plus 1 by K2 into E naught. This is what we called as reciprocal relation. We have taken reciprocal of V and reciprocal of S. Okay, listen. Now in the given problem, a similar equation is given. See, the carbonic anhydrase follows this equation 1 by V, right? And some values are given. So let me write the value as such 1 by V. So what is given? 1 by V equal to 4 times 1 plus 10 by S naught is given. 1 plus 10 by S naught. Okay, yes. Listen, you just multiply this by 4. So we get 1 by V equal to 4 into 40 by S naught. S naught or S simply S. Listen, now you compare this equation. So take this as equation 1. This is equation 2. Now compare these two. Left hand side I have 1 by V, 1 by V. In the right hand side, here I have 1 by S term. Here I have 1 by S term. Therefore, this quantity supposed to be equal to 40. By comparing these two, we can write Km by K2 into E naught is equal to 40. And this number, constant number, it is supposed to be equal to this 1 by K2 into E naught. Why this is constant? Because enzyme is a catalyst here. Catalyst concentration remains as such, correct? So it is a constant. This is also constant. So this is supposed to be equal to number 4. Okay. Now, what is the question asked? The question asked is calculate the catalytic efficiency of the enzyme. Yes, what is catalytic efficiency? Let me write here. Catalytic efficiency is nothing but catalytic efficiency. We usually write as eta. Efficiency eta is equal to K2 by Km. K2 by Km will give you catalytic efficiency. Right? See what I did here. Listen, I just compared equation 1 and 2. By comparing this, listen, I have 1 by S term here. Similarly, I have 1 by S term here. Therefore, this number 40 is supposed to be equal to this quantity. So, Km by K2 into E naught equal to 40. And here, K2 is a constant. E naught is the enzyme concentration. You know very well, enzyme is a catalyst here. So, concentration of the catalyst remains same. So, this is also constant. Constant into constant is constant. 1 by K, that is also, this quantity is absolutely constant. that should be equal to this constant 4. So just take down this. Now, but we see what is catalytic efficiency. Catalytic efficiency is nothing but K2 by Km. Remember this formula, K2 by Km will give you catalytic efficiency. How to find K2? Listen, you take this relation, bring K2 here and 4 here. So K2 is equal to 1 by 4 into E naught. Okay, keep the 4 as such. What is E naught? Initial concentration of the enzyme, it is given in the problem, 2.5 into 10 power minus 9. Yes, just substitute that value here and multiply by 4. You will get 4 into 2.5 is 10. 10 into 10 power minus 9 is 10 power minus 8. Bring the 10 power minus 8 to the numerator. You will get 10 power plus 8. That is the value of K2. So in the place of K2, you put 10 power 8. Then what is Km? Listen, you take this expression, Km by K2 into E naught equal to 40. We know very well. Listen, what is K2 into E naught? Bring K2 into E naught to the right hand side and bring 4 here. So K2 into E naught equal to 1 by 4. So in the place of K2 into E naught, listen what I did here. You keep Km as such. In the place of K2 into E naught, you put 1 by 4, which is equal to 40. Bring the 1 by 4 here. So 40 into 1 by 4 will give 10. This is the value of Km. Substitute this Km here. Right? So 10 power 8, 10 by 10, you will get the answer is 10 power 7. This is the catalytic efficiency of the enzyme as per the given data. Right? So this is the next question. This question appeared in June 2021. The rate constant for the reaction, some reaction is given. For this rate constant is given log K equal to 14.1 minus 10,000 K by T. The question asked here is the activation energy for this reaction in kilojoule per molus. Okay? Yes. How to do this? How to proceed? Listen, you know very well, as per Arrhenius equation, K is equal to A into E power minus EA by RT. Okay? Now, you take ln K. This is nothing. This is not actually log based on K. This is actually ln K. Okay? Or you can also say log K base E. So if you take log K base E for this, log K base E, I will get log A base E and this become minus EA by RT. EA by RT. Now you compare this equation, I will take this as equation 1, this is equation 2. Compare these two, left hand side log K, here also log K. Log A value is 14.1 and this quantity, I have minus here, so leave it. EA by R. Okay, and here T, I have T here. So EA by R should be equal to 10,000. Let me write here. EA by R equal to 1, yes, equal to 10,000. Then what is EA? EA is equal to 10,000 into 8.314. And we want the answer in kilojoule. So what you want to do, divide this by, you will get the answer, now you will get the answer in joule. To convert in kilojoule, divided by 1000. So EA is equal to 1000 means you just cancel 3 zeros. 10 into this, you will get 83.14 kilojoule per mole. To convert joule into kilojoule, you should divide by 1000. Correct. So if you divide by 1000, 3 zeros cancel, you get 10 into 8.04 is 83.14. Okay. Yes. So this question appeared in 2022 June. A zero order reaction, A giving product, rate constant is K. Initial concentration of A is A naught. The time required to consume all the reactant is at what time all the reactant get consumed. And it is given zero order reaction. Okay, yes, how to do this? See, let me write here for zero order reaction, rate constant K is equal to initial concentration of the reactant minus concentration of the reactant at time t. It is equal to initial concentration of the reactant minus concentration of the reactant time t divided by t. This is the rate constant for zero order reaction. Okay. Now what is given? The time required to consume all the reactant, which means A should become 0. If all the reactant get consumed, then remaining concentration of A becomes 0. At what time this happens? Listen. So K is equal to A naught So this becomes 0. A becomes 0 by T. So this is time for completion. Time for completion, because when A is completely consumed, no more reaction takes place. So it is called time of completion. So what is time of completion? Time of completion equal to A naught by K. I have given this formula already while discussing the zero order reaction and all. Okay, anyway, just keep this in mind. So the correct option for this question is option 2. Right? Take 2. This question appeared in November 2020. The question is this. The data obtained from an enzyme catalyzed reactions are 1 by rate against 1 by S, Lineweaver-Burke plot, where S0 is the initial concentration of substrate. The slope and y-intercept obtained from this plot are 50 and 100. This is slope, this is y-intercept. If the enzyme concentration is 0.5 millimolar, then the turnover number of the enzyme is. How to find turnover number? Yes. From Michaelis-Menten equation, we know very well from equation, Michaelis-Menten equation. Okay, we know very well. Rate V is equal to K2 into E0 into concentration of the substrate. You can take S or S0 divided by Michaelis-Menten constant plus S0. Okay, this is the formula. Now take the reciprocal, you will get 1 by V equal to, we'll get an expression like this. I'm not going to write the complete picture, but I'll give you the idea. So you'll get Km by K2 into E0, okay, by S0, right, plus we get this divided by this, S0 S0 cancels, so 1 by K2 into E0. Right? Now, what is Lineweaver-Burke plot? If you plot 1 by V is 1 by rate versus 1 by S0. I have 1 by S0 here. So, if you plot 1 by V versus 1 by S0, what we get is 1 by V, that is 1 by rate versus 1 by S0. If you plot, we get a straight line with a positive slope. And this is the y-intercept. So, what is the slope? Slope is equal to Km by K2 into E0. And what is the y-intercept? Y-intercept equal to 1 by K2 into E0. Okay. What we need to find out is that we need to find out what is K2. That is nothing but turnover number. Turnover number ton is equal to K2 of this reaction. Right? K2 is nothing but the rate constant for the product forming step. Okay, rate constant for the product forming step. Yes, how to do that? Listen, it's very simple. Listen, y-intercept value is available. From this you can find K2 because E0 is available. Right? So what is K2? K2 is equal to 1 by y-intercept into concentration of the enzyme. What is the value of y-intercept given? Y-intercept is given in the problem. Slope is 50 and y-intercept is 100. So y-intercept is 100 into, what is the enzyme concentration? Enzyme concentration is 0.5 millimolar. 0.5 millimolar is given. Milli means 10 power minus 3. So this much molarity. Okay. Now bring 10 power minus 3 to the numerator, it will become 10 power plus 3 or 1000. So 1000 in the numerator by 100 into 0.5. Right? So you can cancel 2020 here. So you will get 10 by 0.5 or 100 by 5, which is equal to 20. So K2 value is 20, which means turnover number is 20. Listen, in all the options, they are asking option in millimolarity, milli per molarity, okay, unit. But what I did in the calculation, I just used 10 power minus 3 here. I removed that millimolar into molar. Okay, so I'll remove this 10 power minus 3. So let's keep this value in millimolar itself. Okay, in millimolar itself. So what we get is 1 by, we multiply this, you get 50, 1 by 50. So what is 1 by 50? 0.10, 0, 100, 2. It is 0.02. This is where the value of K2. 0.02. So the correct option for this question is option A. Okay, turnover number. And this is the next question which appeared in June 2022. The effective rate constant for a gaseous unimolecular reaction A gives P following Lindemann-Hinshelwood mechanism are okay, right, isn't it? So what is actually turnover number? Turnover number. Often it is simply called as ton. TON. What is turnover number? See, turnover number is the number of molecules of product is the number of molecules of product, okay, products, number of molecules of products which are formed at one active site. It's formed at one active site per unit time. Per unit time. This is what we call as turnover number, and turnover number, okay, is nothing but K2. TON. Turnover number is nothing but K2. What is, you can find K2 by dividing Vmax by the concentration of the enzyme, total concentration of the enzyme or initial concentration of the enzyme. Okay, you can find K2 using this formula, right? This is called turnover number. Turnover number, okay. And what is catalytic efficiency? How to find catalytic efficiency? Catalytic efficiency of an enzyme. Okay, which is usually denoted as eta. Eta is equal to K2 value by Km. K2 by Km will give you the catalytic efficiency of an enzyme, right?